Well, I certainly welcome the opportunity to propose my new way to think about quantum mechanics in front of this audience, and I would like to have criticism or questions about it during private meetings or public meetings later. As you know, at the beginning of last century, there occurred two earth-shaking revolutions in physics. Yes?
I think the microphone.
Oh.
Oh, no, it is on.
Everybody hears me? No. Okay. Let me see if I can make it closer. Can you help me put it here so they don't see? Maybe that will be closer.
Working, yeah.
As close as possible.
Okay.
Can you hear me better now?
No.
No?
No.
You can't? Maybe I should speak loud and that's all. Or maybe I have to hold it in my hand, that would be complicated.
No, I don't know.
Well, I know, but how do I make it? Maybe I should use my mustache.
Let's take this off because it's in the way.
Okay.
Let's do that off. Okay, great.
And
Is it just check that it's really loud?
maybe
How
here.
loud is it?
Maybe if I put it here. Try.
Yeah, let me try. Okay.
What?
We're going to turn this.
Ah, okay. Can you hear me better now? More or less?
Yeah.
Okay. So as I started to say, at the beginning of last century, there were these two earth-shaking revolutions in physics that uncovered a whole new phenomena that was not known before when we only experienced the macroscopic world. This phenomena was at first very strange, very against our intuition, which is based on our everyday experience, and we needed to find a way to change our intuition and to be able to tell new stories about what happens in this new ranges of physics. And very soon it developed that the fate of these two theories, relativity on one hand and quantum mechanics on the other hand, the fates were very different. In the case of relativity, Einstein was able to come with beautiful thought experiments that showed that if you just accept the idea that the velocity of light is the same for all observers or the same for all moving frames relative to each other, and that the physical law must be the same for all these moving frames, just based on these simple two ideas, he was able to show with beautiful thought experiments that all the strange phenomena, all the non-intuitive phenomena of time dilation and Lorentz contraction and all the relation between energy and mass, all of this could be deduced just by very nice thought experiments that helped one that goes through them to really be able to develop intuition about relativity. And any student that goes through a good course in relativity will end up feeling that he has now a good intuition about relativity. He can think about relativity from above the mathematics. He doesn't have to rely on solve each problem very carefully mathematically to guess more or less what will happen. Now it's very important that when you have a physical equation that's supposed to describe everything in the world, it's very important to have, apart from the ability to run through the mathematics, to have another language or an intuitive language above the mathematics, because only then you know what interesting question to ask that mathematics to solve. The mathematics can solve any problem, and only if we have some story to tell or some language or some intuition above the mathematics, we can find out and ask the mathematics to solve for us interesting questions. So what are interesting questions or not interesting questions about a given theory is not, the mathematics cannot tell us about it. We need to have intuition that is above the mathematics. It turns out that in the case of quantum mechanics, that happy situation did not happen. And it's that problem that I'm trying to tell you how it's possible to solve and to find really with good stories to tell also about quantum mechanics. Let me show you first the type of story that is told now and why it is not satisfactory. Quantum theory was developed at first in two parallel lines, more or less, one by Heisenberg, that started first, and then by Schrödinger. When Heisenberg started his approach to quantum mechanics, he had a very fantastic intuition that he had to try and organize the type of information that he knew about spectral lines and about energy levels, etc. He found that if he uses a crazy notion of some rectangular way to put the numbers on and play with them, he didn't know what he was doing actually mathematically. It was born that came by one day and looked what he's doing and said, you know, what you're doing is really something that mathematicians call mathicid. He invented the matrix formulation without knowing about it, just as an insight from the physical experimental evidence about quantum mechanics. So anyhow, this was one development that happened a few months before Schrödinger, and when he came out with it, many people tried to help him to solve problems with this matrix formulation. And it turned out that it was easy to solve harmonic oscillators, to solve hydrogen atom, and few other things. But the minute when they tried to solve more complicated problems, like more than a single electron atom or other problems, it became more and more difficult to do it. And then suddenly came Schrödinger, and Schrödinger had an intuition from what de Broglie suggested. And I want to point something about this step, because you will see already there how some difficulties entered into that picture that were missed. What did de Broglie do? De Broglie looked at what was discovered about electromagnetic fields, classical electromagnetic fields. But as you know, Planck was able to show that if you assume that the energy exchange between the electromagnetic field and other systems, like the walls of a black body, if this exchange in jumps proportional to the frequency, and now it's called jumps of h nu or Planck constant times the frequency, then one could explain the experimental thing that happened there. Einstein came there and said, no, it's not only the jumps. He said, actually, we have to think about the electromagnetic wave as also having classical properties. Namely, the energy of the electromagnetic waves doesn't change continuously, is not continuous, it's made out of lumps of energy, and that's why they are called quantum, because they cannot be divided anymore. And these are equal footing. We have now suddenly a description that in classical physics was just wave, and in quantum mechanics we have to say we have two important features of this situation: classical particles and waves. But I think what was missed at this point by de Broglie when he came and tried to adapt this picture for classical particles, what was missed is the fact that the wave property of the electromagnetic wave, and the number, which are the number of photons, the photons, they are complementary to each other. If we measure the wave property of the wave, like electric and magnetic field, we necessarily have to change the number of the photons. So to say that a single photon also has wave properties is a mistake. What we can say in the case of understanding deeply the electromagnetic situation, we have two complementary pictures. One is the pictures of the wave properties, which are the electric and magnetic fields at each point, and the other is the picture of photons. And the two pictures are not going together. We can't think of a single photon having also wave properties because of that explanation. But then the Broglie came, not noticing this difficulty, and he said, look, if in the case of electromagnetic field, we saw that there are also particles, maybe we could have particles and we have to quantize them, they should have also wave properties. So if a particle has a momentum p and the energy E, then maybe this particle can also be described as a wave that has a wavelength and frequency corresponding to the connection that was found for electromagnetic case. And then based on this, he was able to write a very simple differential equation that just used that intuition, and we develop a new approach to quantum mechanics, where the vector in Hilbert space is described by its amplitude in the position representation. We have the function that's called the wave function of Schrödinger. It's really mathematically the amplitude when you expand that vector in Hilbert space in the position representation, namely the amplitude of what are the amplitudes for each different vector, any vector of position. So that wave can then be thought about only as mathematical property, namely expressing the vector in Hilbert space as superposition of amplitude. But because the equations of motion for Schrödinger were so simple, and the description of the whole quantum system was then just by this wave, then people decided maybe that is really what's happening. And then there was an idea to say that indeed a classical particle, when you quantize it, behaved not only as a particle, but this same particle behaves also as a wave. And then the question was, what is the meaning of this wave? And that is where the problem came. If we think about the particle, like an electron, it has a charge, it has a mass, and we say that this particle is described by some wave. That means that in some sense the particle is spread over this region. And indeed, when Schrödinger first tried to think about what the waves mean, he actually thought that these waves mean that the charge and the mass of the particle are spread according to the density of this wave. We'll speak about destiny later. And he was very happy that he found the solution for harmonic oscillator. He found the solution of wave packet that doesn't spread, moves around like a classical particle with a little bit of width, and say, aha, this is really a description, a physical description of something that is really spread over this region, and it moves, and fine. So we don't have a point, but we have a mass and charge that are spread. Actually, people even in classical physics, when they try to avoid the problem of the infinities that come if you have an electromagnetic field theory, you have a point charge, you know that immediately you get infinities of energy because the total integral of E square becomes infinite. So already in classical physics, people say that particles must have some spread. They couldn't be a point particle. So it was not a strange idea for Schrödinger to think that perhaps this is just what happens in quantum mechanics. We have a particle that is spread, and it continues to move like this spread object. But very quickly, people that looked at that interpretation realized that it can't be true, because the minute when you speak about another problem rather than harmonic oscillator, that wave doesn't stay put together, it spreads all over space quite quickly. And now if we still want to say that this spread indeed is a physical description of densities of mass and charge, this should mean that we could come to a given region of space and find there parts of the electron, parts of the mass, parts of the charge, according to how much density was there. And that, of course, is not true, because any time that experiment was made, all the mass of the electron and all the charge of it was found just at one location, independent of what was the spread before. So therefore, that wave function could not be thought about as a real spread of charge and mass according to its density. So what could it be? Then Bohren came with the idea to suggest that maybe what this wave function describes is not something that is actually there, but it's the probability to find the electron with all its mass and all its charge at a given point according to the size, or absolute value square of the size of the wave function. That could have been a legitimate approach, but it could not solve the problem of the interference, because people say the following. If I had, for example, a two-slit experiment, this is the thing that gives us the biggest headache when we try to understand what's going on in quantum mechanics. So people say the following. Look, we first have the Schrödinger wave, a plane wave comes here. We don't pretend that there is a real charge distribution here. It's just a wave that we don't know what it means. This wave comes here, and this wave comes here. And we find, after we collect many results, each result that we collect here is really a probability to find all the local properties there. That's fine. But if we try to find out why there are some locations here where we don't see anything when the two slits are open, and we see something where either one or the other is open, we must then say that the only way to explain this is like a true wave. It's like something that's moving here, and at the same time something that's moving here. So they gave the name of this something amplitude, and they invented the story that if we don't look, there is this mysterious amplitude that goes both places in order to explain the probability here. When we look, we only have probability. But when we don't look, we have in the past this entity, which is called amplitude, and we don't have any way to think about it, apart from saying that we need it in order for later to see probabilities. So this is the reason where Feynman, for example, said that he believes that no one ever will understand the mystery of quantum mechanics. No one ever will, because no one will be able to understand what is the mysterious thing that goes here. We cannot describe it in physical language, we can only describe it in mathematical language. Mathematically, we say, look, we have this thing that propagates, it tells us what is the probability here, that is the physics. Here, what's going on here, it's only mathematics. Now, making a jump in many years, some people feel that they now, including that one that sits there, that's named Weizmann, they believe that they can understand what it means to have this particle being, this wave being in both places. They say, in fact, the particle is in both places. And when we look at these particles, for example, we do an experiment, the Sterr-Gerlach experiment, we see a big macroscopic spot on the photographic plate if the electron went up, or if the electron went down because of the opposite spin. We see a big macroscopic spot down. When we look at it, we actually found that both of them were there. But we found it in a very mysterious way. They did something in both places, the particle in both places, But when we look at it, our mind goes into two states of memory. One of them remembers one spot, the other one remembers the other spot, and both of them coexist without knowing each other. So see what's going on here. We start with a little problem of a microscopic system that we did not know what it means for it to be at two different locations. And in order to explain what this is, we might even say the whole world now, the whole macroscopic world now is in two different locations. That's the only way we again don't have any intuition what it means for me. For example, imagine that I decide whether tomorrow I will come and give a talk here or tomorrow I will take a rest. So I decide to throw a coin. If the coin comes up, I will come here. If the coin comes down, I will not come here. That's a classical coin. But I could instead use a quantum coin. I will take a spin half particle and arrange that with alpha probability will go up and with alpha probability goes down. Then I look at the spot. I say, aha, the spot is up. I will come here tomorrow. Spot is down. I will take a rest. Now what happens? According to this new interpretation, I am now in two different locations tomorrow. I'm here, and at the same time, I am resting at my apartment, doing something much nicer. So what's going on here? If I believe that, I have to say, I have to develop some intuition what it is for me to be in two different locations. There is no way for me to develop this intuition. So, and there is probably, which I can prove, and eventually will do it, there is no experimental ever possible to show that I was in both two. Lev Weizmann believes there will be some super technology that will be able to show that you can interfere these two possibilities of me being here and me being there. I am willing to bet, and I'm going to spend some time on it, to show that in order to do this experiment, we have to collect so many microscopic devices that we end up with black hole before we get there, and I'm going to do that. So suppose we can prove that there would never be a way to check experimentally that we are in these macroscopic two worlds, and the more bigger things are even more difficult. So that would not stop these people to say, okay, we don't prove it, you can't check it, but the mathematics tells us that that's the case. So we believe the mathematics, that indeed we split into this world, and we get this picture becoming more and more complicated. We believe the mathematics. But that means that we become slaves of the mathematics. We accept what the mathematics is telling us without really understanding what it means. So I think that if we can find another picture that will explain the same things, the same prediction, that we will not have to go through this situation where we have to believe the mathematics to tell us stories that we cannot develop intuition about it, we will be much better off. And I claim that that can be done, and that is the purpose of my talks here. So the way to start this new direction of trying to explain quantum mechanics in a way that we could develop a good story for, I claim that we have to start with the Heisenberg representation and pay much more attention what it's trying to tell us. I will end up saying that the Heisenberg representation is the correct way to think about what's happening, and the Schrödinger representation is just a mathematical way to help us to solve the Heisenberg equations of motion. So even though this mathematics is very nice, and we think we have simple intuition about it, this is intuition about the mathematics. The intuition about what happens really physically that will help us to think about the mathematics is going to be done by the Heisenberg representation. So let me start the story now. If I have a vector in Hilbert space psi, there are two ways to describe what this vector means. One way is to expand this in complete sets of eigenvectors to choose a particular representation and say the vector is characterized if we know all the amplitudes. But there is another way to characterize the vector by looking at the following question. Let us look at all the observables, each physical observable, which for one party is a function of x and px, well, these are operators. Let us look at all the observables for which psi is an eigenvector. This is the opposite question they usually ask. Usually you ask the question, if you are given an operator, what are all the eigenvectors of this operator? Now I ask the opposite question. Given the vector, what are all the eigenoperators of the vector? And so we have a complete set of operators, f of x, fi of x and p, such that this is equal to a number, fi, this is just a number times psi. Suppose we look at the collection of all such operators that satisfy this condition. It turns out that this collection has the following properties. First of all, if I know all of them, I will know exactly what psi is. They uniquely define what psi. Second, the collection of these operators, which are in fact, they are like matrices, if you remember, it turns out that if fi and fj are in this set, then the product fi fj, if I want to be Hermitian, the commutator times I and the anti-commutator of these two are also belong to the set. The sum of any two belong to the set. So the set is closed under the algebra of these operations. And as I said, it defines completely the state psi. Let us see just an example that will show what we are talking about. Suppose we take a finite dimensional Hilbert space, say with four dimensions. So the vector in this Hilbert space will be 1, 0, 0. And we ask now, what are all the matrices? The set of all operators are now discussed by Hermitian matrices. We ask, what is the set of all Hermitian matrices for which this vector is an eigenvector? And the answer is very simple. Any matrix that has zeros here, and non-zero entrance here, zeros here, and arbitrary entrance here on this point. So all such matrices have this as a common eigenvector. And this is the only common eigenvector, because if I take any other entrance here, some of these matrices will change it. So we can say that instead of speaking about vector Hilbert space, we can speak about the set of all eigenoperators, or the set of all deterministic observables. Then those deterministic observables can be measured without any disturbance of the vector. We don't run into collapses, we don't run anything. So we can say, if we just look at this subset of matrices and look at their time evolution, instead of looking at the time evolution of the vector by using the Schrödinger representation, we look at the time evolution of the Heisenberg operators according to the Heisenberg equation of motion. It's more difficult to be done, but it can be done. Then it will be an interesting situation, because we say we can follow all what's happened to the vector in Hilbert space as a function of time by looking only at the properties of observables that can be observed just like classical observables. They don't disturb the other. I can measure all of them and find out what's happened to the physical system, just like in classical physics. So the question is now, there must be some difference between classical physics and quantum evolution, and now we must be able to find the difference by just looking at the difference between the dynamics of this subset of observables classically and the same observables quantum mechanically. And that is where the big surprise comes, and the beginning of understanding more deeply quantum mechanics. suppose I look at the situation of the two slits just after the particle comes from the two slits. So I will, for simplicity, I will discuss just a one-dimensional analogy that I have a wave packet here. This is representing something comes out of one slit. I have far away a distance L, which is the distance between the two slits. I have another wave packet. And let's assume that this one, and if I translate this one to here, I will get this one. Call this psi left, and call this psi right. And consider the vector psi alpha, which is equal to psi left, plus e to the I alpha psi right, divided by square root of 2. So we have now a whole collection of different vectors, and we can ask what are the eigenoperators of each one of them. And it turns out that if we try to write the eigenoperator f of x and p as a polynomial of x to the n times p to the m, all such polynomials will not be suitable to become deterministic operators. Because if we calculate the average of f for psi alpha, we'll see that it doesn't depend on alpha. And if it doesn't depend on alpha, it could not serve as a deterministic operator. Deterministic operator average must depend on alpha if it's for the vector alpha. So let us check. Suppose I look here at the integral of psi 1 star of x plus psi 2 star of x e to the minus I alpha times x to the m d n dxn times I to the n. I take h to be equal to 1, or minus I to the n, times psi 1 x plus e to the I alpha psi 2x dx. After normalization factor, that is the average of this operator, x times p, and we want to see whether that average depends on alpha or not. And the answer is that it doesn't depend on alpha. Why? Because if we look at the contribution that depend on alpha, these are the mixed contributions. In this one and that one, that average, that are the contribution in the integral depends on alpha. If I take psi 1 doesn't depend on alpha, psi 2 and psi 2, here minus I alpha, here plus I alpha, so it's cancelled. So the only thing that will depend on alpha are the mixture. But remember, we have here psi 1 is here, psi 2 is here. Even if I take any derivative of psi 2, it will still say different from 0 here. So the product of that times that gives me 0. That means that this thing will not be sensitive to alpha, and therefore if I look for deterministic operators that will be sensitive to alpha, I can't write them as a polynomial like this. I have to look for something new. What is the thing that is new? Suppose I look at the operator e to the I PL over H bar, PXL over H bar, and I can add later its complex conjugate to get the cosine of it to get a remission operator, but let's just look at one of them. Suppose I try to calculate the average of this operator from the situation that we discussed before, and you can easily check yourself the average of this operator, because this operator translates one wave function by distance L to the other. That average will depend on alpha. In fact, the average of this operator will be 1 e to the I alpha over 2. Now, the first question is, how is it possible? How is it possible that all the polynomials of momentum don't give us dependence on alpha, and the average of this operator does depend on alpha? We know that we can write the exponential, we can expand it as a sum of px to the power n, x to the power n, h bar to the power n, over n factorial times I to the power n. So here we have an expansion of this operator by all these polynomials. And we say that none of them depends on alpha, and nevertheless the sum does depend on alpha. How is this possible? The answer is that we have a situation that the wave function that we are talking about is not analytic, it does not have Taylor expansion. Meaning that if I look at this wave function, look at all the derivatives of it, because of 0 here, anything that I can find here will not tell me whether there is something here or not. So therefore, these things does tell us what happened. Each one of them doesn't tell us, so that means that the average of this is not equal to the sum of the averages. When you have a non-Taylor expansion situation, that is what happened. The question is then, how do I prove that e to the I pxl over h bar is a linear translation? The answer is, if I know that psi of x has a Fourier transform, I can go, instead of looking at it as a positional representation, I can look at the same vector psi as an integral of some amplitude and momentum times eigenstate of momentum. I know the connection between this and that one is the Fourier transform of the other. So if I can Fourier transform this, I know how to write the vector psi in the momentum representation by having this amplitude. So the only thing that I need to know in order to have this is to make sure that psi of x has Fourier transform. And you look at these two functions, you see it has Fourier transform, so I can certainly write in this way. Now when I apply the operator e to the IPL over h bar on this, because these are eigenstates of the momentum, it becomes just the numbers. And then it means that psi of p will be multiplied by e to the IPL, and then I can transform it back and see that x is a translation operator, even though I couldn't do the power expansion. Okay, so we say we found something interesting, maybe. We found that when we want to look at the time evolution of these two wave packets, instead of evolving them in time, we freeze them, and instead we look at the deterministic operators and involve them in time, according to the Heisenberg equation of motion. And the question is now, will we see in this Heisenberg equation of motion something that will be unique to quantum mechanics that will tell us why this behaves in a new way that has no classical analog? Classically, if we have a probability of being here and probability of being here, we never see interference. Quantum mechanics, we have amplitudes here and amplitudes here, we see interference. We are now able to describe the time evolution not by propagating this wave, but instead by propagating in time the deterministic operators. And we have seen that those behave essentially like classical systems, because those operators don't have uncertainties, they don't cause collapse, they just evolve according to their equation of motion as if they were classical properties. So there must be some difference between the time evolution of this set of observables if we look at it classically and we look at it quantum mechanically, because only there we could see a possible difference. And if we see this possible difference, it will have nothing to do with the question of waves, nothing to do with collapses, nothing to do with uncertainties. It has to do just with a pure difference in the dynamical equations of motion quantum mechanically compared to classically. So what are the dynamical equations of motion classically, and what are they quantum mechanically? And I will already now anticipate what will be the main theme of my talks. The main theme of my talks will be that the correct way to start, going from classical physics to quantum mechanics, is not by looking at the kinematics and saying that it waves, etc. You look at the dynamics. There is the classical dynamics, there is the quantum dynamics. I will show that just by looking at the difference between the classical and the quantum dynamics, we could, from that, this will be our starting point, like the velocity of light being the same. The starting point here will be that the difference between classical and quantum dynamics is the difference in the dynamics. And once we understand what this difference implies, we will see that the uncertainty follows, interference follows, all the strange properties that we see in quantum mechanics follow just from this change in the dynamics. So how does it work? In this case first. I have a few more minutes.
Do you want questions at the end?
Yeah. So.
And then just maybe speak for 2 more minutes.
Very quickly. Okay. So. So let me remind you. In classical physics, we have the Hamiltonian equation of motion because we want to discuss the Hamiltonian equation of motion classically are the ones that are easy to compare with quantum mechanics. So the Hamiltonian equation of motion are x dot is equal to the HZP in px, and px dot is equal to minus the HZx. And from this we deduce that if we take any function of x and px, its time derivative is equal to the f dx times x dot, which is the HDP, plus the FDP times p dot, but p dot is minus the HDX, so we replace it by minus the HDX. This combination of two functions written this way was given the name Poisson bracket. So the Poisson bracket between two functions of x and p is defined this way. So we can say that classical physics is characterized by the fact that we have observables, which are functions of x and p. We have Hamiltonian that define for us the dynamics, and the equations of motion classically are given by the Poisson bracket between f and h. Now, quantum mechanically, the difference is the following. If we have a function now of operators x and p, and the Hamiltonian, which is a function of another function of operator x and p, I forget, I don't take your time because it's irrelevant for our main discussion. Now the equation of motion is that the f dt is equal to 1 over I h bar df dt is equal to the commutator between this, which is fh minus hx. So this is commutator, this is Poisson bracket. So first of all, there is a nice thing. We have brackets in both cases. There's some anti-symmetry that works in both cases. There are nice features that look the same. If you look at the difference between the Poisson bracket and the commutator, and you look at simple, you look at the Hamiltonian p squared plus v of x, and you look at the equation of motion for the operator x dot, for the operator p dot, you find that there is no difference between the commutator and the Poisson bracket. In fact, at some place, Dirac wrote that the fundamentals of the change in the dynamics between classical and quantum mechanics is not significant. If you go to more complicated thing, you have some corrections to order of h bar, but they are very small corrections. But it turns out that this is missing the most important point, and I will just say it now without proving all of it, and that will be the beginning of next lecture. It turns out that when you look at the variables that are relevant for interference, as we have seen, which are variables like cosine p over p0, periodic function of momentum, where p0 is equal to h over L. I write it as p0 because I want to look at it without measuring h how would this behave classically and how would this behave quantum mechanically. And here we see a fundamental difference. It's exactly for these operators, which are relevant for the interference, these kind of observables have fundamentally different behavior classically and quantum mechanically. Classically, their equation of motion will be still local. Local in the sense that if I want to change something, I have to see a change in the momentum itself. That means I must put a force at the place of the particle is in order to see a change in that classical observable. But if I look at the same observable and look at its equation of motion quantum mechanically, lo and behold, I see a truly non-local behavior. The equation of motion for this, we know not if the force is acting on the particle, but we will know if there is a force at distance of the order of L away from the particle. So we discover now that there is a fundamental difference between classical and quantum mechanics. Classical physics is always local. Quantum mechanics is non-local exactly at the time when we consider variables that are relevant for interference. So that opens a completely new possibility. Up to now we saw that if the particle goes to one slit, it will never know whether the other slit is open or not. But lo and behold now, if quantum mechanics tells us that there is some observable, which is the modular momentum or the cosine of the momentum, this observable has no local equation of motion. This observable is the thing that will tell us what will be the interference later. So we now can have a completely new picture. The new picture is we have a particle that goes to one slit, and it knows whether the other slit is open or not, because it has a property that has no local equations of motion. The minute when I say that, you can start to attack me immediately. Up to now, we knew always that everything has to be local, because if it's not local, it will violate causality. It will be all kinds of terrible things. It took us so long to come from the time of Newton that we saw that there are non-local equations of motion. Then came Maxwell. Then after Maxwell, we learned that any effect of a particle must be due to something coming and touching it, like the wave, the electromagnetic wave coming to particle and say, you have to feel the force. And now suddenly, I come and tell you that we come back. We come back to introduce non-locality again, like a wave. First locality, then non-locality, now locality again. What's going on here? How can it be consistent? We have learned very carefully that nothing non-local can be consistent with causality. That is the beauty of quantum mechanics, how it managed to solve exactly that problem. And I'm not going to tell you how it does it, so I will be sure that all of you will come tomorrow.
Some questions?
Yeah.
So I had the pleasure of having dinner with C.A. Yang recently.
Yes.
And your name came up because everybody agreed that the Aharanov form effect is the best example of why we have local phase invariance. Not non-local, local.
Yeah.
So I asked Yang, why local phase invariance? And he said, well, Dirac, at the end of his life, said, oh, I always thought classical to operator was the big deal with quantum mechanics. But now I don't think that anymore. He says, now I think it's phase.
Yeah.
So
No,
now
then-
I come to you and
Good.
I say,
Good
why
question.
local phase invariance? Oh, I'm sorry, I didn't finish the story.
Yeah.
So I said, oh, but CN,
Yeah.
Frank, why do you think things are local phase invariant? Okay, this is the key point. He said, God only knows. So I ask you,
Okay.
local phase invariant.
Now you put me in a very bad state, because if I say I know, then I'm good. I don't. So I will answer it to you at the beginning of next talk, okay? So you come also. I will answer exactly this question. It's a good question, but it takes more few minutes to explain it.
I'm a bit curious. You mentioned about operators and states, and I liked your idea, basically the eigenstate relation, the mixer relation. But that's very unintuitive, I would say. How would you think about this relation about an operator and the eigenstates?
Well, what is intuition and not intuition is depending on the function of time. What you look now, non-intuitive situation, I promise you, maybe even at the end of the week we'll be more intuitive, but much later definitely. So wait about the issue of intuition and see some more information, okay, before we can talk about that.
Yakir, you expressed your objection to many worlds. Can I hear your objection to dynamical wave function collapse?
Oh, I will come to that also.
Oh, you can do it a little later.
No, the point is that I will show that in this new approach that I'm developing, it's very important to talk about two boundary conditions for a quantum system instead of one. And when I talk about that, then I can arrange a way to get the possibility of getting rid of the many worlds by choosing just one branch, by having past and future boundary conditions in the universe. But wait, we'll discuss it. Okay? I have an answer to that too.
Any more questions?
You have a question?
What you just mentioned before about these tailorless wave functions, wave packets are not Taylor expansive, but they do the Fourier structure.
Yeah.
So what is the
What?
intuitive meaning of this difference?
Well, it's a mathematical issue. Taylor expansion needs that the wave function will be analytic. Fourier transform, it's not necessary. We need non-analytic wave functions because each time we intervene with the system, we really introduce non-analyticity. So it's better that we learn to think about wave functions in a language that avoid this problem, and that is the interference with language. Okay?
So we should stop there. So thank you very much.